Yang. I'm the lead architect in OpenSTS, an open source project under Linux Foundation. I'm also a co-lead in the volume snapshot project in Kubernetes, SIG storage, and a tech lead of the CNCF storage SIG. This is my co-speaker, Takei-san.
Hello everyone, I'm Seiya Takei from Yahoo Japan. My main job is the operation of software-defined storage, and in past I was involved in private cloud based on OpenStack.
Here's the agenda for today. So first we'll do a brief introduction to anomaly detection, and our focus is on doing anomaly detection in storage performance. And Takei-san will talk about Yahoo Japan's use cases. We'll talk about telemetry, a project that integrates with Prometheus and Grafana, collecting performance metrics from storage backends. And we're doing anomaly detection using those data collected from the metrics module. And we'll do a demo. So what is anomaly detection? Anomaly detection is a technique used to identify unusual patterns. Can you tell which one is an unusual pattern in this diagram? I hope it's I hope that's obvious, right? The red color sad face stands out in a group of happy blue faces. So there are different categories in anomaly detection. The first one is point anomalies, which means a single data point is very far away from the rest. For example, you can detect fraud detection just by looking at the amount spent. Second category is contextual anomalies. So the anomaly is context specific. This is typical in time series data. So you spend a lot of money on food every day. During holiday season, may be normal, but otherwise it may not be normal. And the third category is collective anomalies. So meaning that a group of data collectively identifies an anomaly, but if you look at a single data point in that group, that may be normal. So if you're spending money to buy a large number of expensive items on a single day, then maybe that's not normal, but if you just look at a single transaction, that may be okay. So there are different use cases in anomaly detection. It's used in intrusion detection to find out if there is a hack by looking at the network traffic patterns. It's used in medical health to see if there's a tumor by doing a scan. It's used in fraud detection. So if you usually don't travel abroad and suddenly your credit card is used in a different country, then that transaction is likely to be rejected, and then until you confirm that it is really you, then you wouldn't be able to use your credit card. And it's used in fault detection to detect if there is any problem in a medical unit, like a newly built aircraft. And of course, it's used in storage to find if there is any problem in storage systems. For example, to check if SSD has worn out and needs to be replaced. And it's used to find issues in storage performance as well. So it's challenging to detect issues in storage performance because many things can go wrong. You could have disk failures, you could have a rewrite IO errors, or some port problems, configuration issues, battery problems. So we need to look at metrics collected from different ways. Look at the IOPs, bandwidth, and then look at the cache hit, and so on. We need to collect data from multiple dimensions and correlate them and identify bottlenecks. So that's what we are trying to do. We're trying to collect metrics on storage performance and trying to detect anomalies using this data. And Takei-san is going to talk about use cases in Yahoo Japan.
Yahoo Japan is one of the biggest company providing web services in Japan. The number of services we providing is about 100. In our data centers, many virtual machines and containers are running. 140,000 VMs are in infrastructure as a service, 30,000 containers are in platform as a service, and 390 Kubernetes clusters in container as a service. In OpenStack environment, we are using storages for Cinder, Swift, Manila. In Kubernetes environment, we are using storages for persistence volume. OpenStack and Kubernetes clusters have each storage. So if the number of clusters increases, the number of storage also increases. Moreover, there is bias in Kubernetes clusters in capacity between OpenStack or Kubernetes clusters. This means some clusters have enough free capacity in storage, but some clusters have not enough free capacity in storage. In future, we hope to manage storages centrally by OpenSDS. The storages managed by one OpenSDS cluster can be used by multiple OpenStack and Kubernetes clusters. Then, if telemetry and anomaly detection are managed by OpenSDS, storage management becomes very simple. Recently, we are using software-defined storage such as Ceph and Provide. Now we are experiencing that SDS is difficult to operate. SDS is configured by distributed system. It is very important to clustering SDS servers. So we should manage severely the health of servers, networks, and so on. This means that telemetry and anomaly detection is very important function for operating SDS.
So Takei-san has talked about the use cases, and then they want to use telemetry and anomaly detection of OpenSDS. The OpenSDS is an open autonomous data platform. So this shows the project scope. So there is a northbound plugin to support container orchestration systems, and it provides a common control plane to manage block, file, and object storage. Our focus today is this purple block here, insight and intelligence service. This shows our road to autonomous data platform. So, and each stage, what we want to achieve. Right now, we are at the first stage. So we are working on telemetry and anomaly detection, collecting metrics from different storage backends, and doing analysis on them. And then eventually, we want to build a data platform that is self-managing and self-optimizing. This is the architecture diagram of telemetry. So here we have an API server that has a post and get APIs. And then there's a controller. And then there's a dock that is like a docking station that hosts metrics drivers for LVM, Ceph, and other third-party metrics drivers. On the dock, there is a collector. So let's show here. The collector collect metrics from different metrics drivers, and then that data will be sent to, will go here. There's an adapter here that includes a converter and exporter. So the converter basically converts the matrix into a format that can be understood by the destination, and exporter emits the data in a format that can be retrieved by the destination, so like Prometheus. We also have integration with Kafka.
Metrics collector gets IOPs, bandwidth, latency, CPU usage, and custom metrics for volume per disk controller resources. For example, IOPs or volume, and bandwidth of disks, and so on. On-premise storage, such as direct attached software defined enterprise is supported. And also cloud storage such as Ceph S3 Gateway, AWS, Azure, Google Cloud Platform is also supported.
So since we integrate with the Prometheus, I just want to quickly go through this Prometheus architecture diagram. Prometheus has a server that includes 3 components. It has the retrieval component that periodically scrapes data from an HTTP endpoint configured on the exporter, and then saves that in the database, which is this TSDB database. It saves the metrics with a timestamp. And then the third component is this HTTP server that can handle HTTP-based requests using PromQL, which is a Prometheus query language. And then also Prometheus has a alert manager. So this shows a little bit detail of our telemetry's integration with Prometheus. So if it's a post request, the API server gets it, pass on to the controller. Controller will send that to the collector. Collector communicates with the metrics drivers, get the metrics, and then the exporter will emit that metrics. Prometheus server will be pulling those metrics. And if it's a GET request, so that assumes the data, the metrics is already there in the Prometheus database. So the controller will just do a conversion using the PromQL and get that metrics from the Prometheus server. So our telemetry module doesn't have a database itself. We just use the database in Prometheus. But our anomaly detection module does have a database, which I will cover a little later.
The metric interfaces are defined like this. Struct collect metrics desk has type of driver such as LVM, Ceph, and so on. Struct get metrics desk has instance ID, metric name, start time, and end time. Instance ID is volume ID in example. Struct metrics spec has instance ID, instance name, job, labels, component name, unit, aggregate type, and metric values. Actual metric is struct metric. It has only timestamp and value. There is LVM exporter in OpenSDS to collect LVM metrics. LVM exporter uses LVM system activity reporter and IOStat in its node. Supported metrics is currently IOPs, read throughput, write throughput, response time, service time, and utilization percentage for volume and disk resources. In Ceph, the Ceph exporter is already exists in Prometheus website. Existing Ceph exporter in Prometheus is used to collect Ceph metrics. Only cluster metrics is printed in slide as supported metrics because the slide has no enough space, but other metrics can be collected. Food, volume, Ceph components such as OSD, monitor, and so on. In Ceph environment, so many kinds of metrics are supported. This picture is LVM metrics focused in last 6 hours in Grafana dashboard. This metrics is collected by LVM exporter in OpenSDS. LVM volume is of utilization, response time, write throughput, read throughput, IOPs, and service time are placed. This picture is LVM volume metrics focused in 30 minutes. There are input and output in LVM volume about 10 minutes.
Going back to this diagram, so our telemetry module exports the metrics, and then Prometheus will retrieve those metrics. Prometheus also has an alert manager. So you can use the Prometheus alert manager in two ways. You can configure alert rules in Prometheus, and then when it passes that threshold, Prometheus will raise an alert on the alert manager. So I think this example shown here, maybe it's difficult to see, but this is the one. When you say disk space 10% free, then it will raise an alert. And then the second way is to use the REST API interface of Alert Manager. You can raise a custom alert. So our anomaly detection module uses that. So the example shown here, that's the same disk running full. That's a custom alert. So we have an adapter that will also send data through Kafka, which will be received by the anomaly detection. So this shows the architecture diagram of anomaly detection. So the metrics collected will go through Kafka, sent to the data parser component. Data parser will parse data and save the data in the database. And we also have a data generator component that runs cron jobs that can be configured. You can either run post or get requests and get those data from the telemetry module. And the training service will use data from the database, run different algorithms and pick an optimal model. And then the prediction service will be using that selected model to run analysis and produce results. And if anomaly are detected, it can send a post request to the telemetry, and telemetry will send an alert to the alert manager. So there are different algorithms used in anomaly detection. There's a classification based. It basically uses a classifier to distinguish between normal and abnormal data points. There is a nearest neighbor-based algorithm, which assumes normal data reside in a cluster, in a neighborhood, and then the anomalies occur in place far away from closest neighborhood. And then there's a clustering based, assuming that normal data reside in a cluster, and then the anonymous data points does not belong to any cluster. And there are also statistical models like Gaussian and regression, and also information theoretic and spectral. So we are going to use the clustering-based algorithm called DBSCAN and the Gaussian model in our testing. So a Gaussian model is a classic statistical model, assumes that data forms in this bell shape, and you should use you should specify a threshold to differentiate between the normal data points and anomalies. And DBSCAN means density-based spatial clustering application with noise. So we have a diagram here. So basically, the DBSCAN algorithm takes two input. One is the radius of the neighborhood around the core point, and then the second one is the minimum data points in the cluster. And then based on those two input parameters, it divides the data into three categories: core points, border points, and outlier. So this blue dot in the middle here that's a core point because it is in a cluster with more than 5 data points. And then the green dot there is a border point because it is in a cluster of less than 5 data points. And then the red one is an outlier because it is not in a cluster with any other data points. So we run the Gaussian model with the data we collected from LVM. So we collected 6 different metrics from LVM, but we only used the 2 to show this. It's easier to display here. So we used the volume level metrics, IOPs, and latency here. So we basically collected that in 2 days, and then we get 6,000 data points after removing some zeros. And then we also used the DD, and then we used the Bony to generate some workloads. So yeah, so the blue data points, those are in those are the normal data points, and then the red ones are outlier. And then this is the from the DBSCAN using the exact same data. So this shows, so the bigger circle in red, those are core point, and the small point in red, that's the border point, and the black dots are anomalies. So this actually looks a little similar to this. So the shape of it looks a little similar. So there are some anomalies detected. Actually, some are detected in both figures, but some are different. We also run those tests using Ceph. So we set up a Kubernetes cluster, and we have an OpenSDS installed there. And then we also set up a MongoDB. So MongoDB is running as a stateful set. There's 3 replicas, and it is running on a volume provisioned by OpenSDS CSF plugin, and the backend is Ceph. So here, as it shows, just the sort of class is the OpenSDS CSF plugin, and then we collect metrics from the Ceph exporter, Node exporter, and MongoDB exporter. So this is what we get from Ceph. So we don't have enough time to get more data, so this is like 6 hours. Then we get 6,000 data points after removing zeros. And we used 2 different MongoDB performance tools. One is a workload driver, the other is a MongoDB multi-threaded performance test tool. We use those to generate some workloads to do some insert, deleting, update, and find. So we get 5 clusters here, but most of them are actually in one large cluster that's in the color, the red color. The rest of them, so like there's some smaller clusters like this yellow, orange, and green. Those are smaller clusters. Most of them are at the bottom. So there are a small number of, there are some anonymous data points. Those are the black dots there. So this is actually the same data, but this is just one section of that. This is only 1,000 data points. So when we use this, it just has one cluster, and then most of them are in this one cluster, and then there are some the black data points. Those are anonymous. And then, by the way, this is the Ceph client IOPs, because we don't get the volume level performance metrics that we used for LVM. So for Ceph, we just use this client IOPs. And this is data collected from the Node exporter. This is the Node memory available in megabytes. So this also shows just one large cluster, and then a small number of anonymous data points. So this is from MongoDB. This is the global log current queue. This is actually not what I have expected because there is a gap there. So it forms two clusters, and then there was a few anonymous data points. So my assumption is because we generate a lot of load, maybe the system cannot handle it, and for some reason there was no data for some section of the time. So Takei-san is going to show a demo in telemetry.
I made telemetry demo environment in our private cloud, and I captured this movie. This is OpenSDS dashboard. It has a monitor tab. In Prometheus setting, there is the LVM exporter. Jump to Grafana dashboard. The metrics of read throughput and write throughput and IOPs and response time are placed here. And show the volume information using OpenSDS command. Read from every LVM volume using DD. Back to Grafana dashboard. As you can see, read throughput is increases. Jump to Alert Manager dashboard. There is no alert currently. Next, write to LVM volume using DD. In Alert Manager setting, I set the write throughput alert for LVM. If the volume write throughput is over 1 megabyte per second, the alert is occur. Write to LVM volume using DD. Already the write throughput is over the 1 megabyte per second. Back to Grafana dashboard. As you can see, the write throughput is increasing. In Alert Manager, there is a write throughput alert because the volume write throughput is over 1 megabyte per second. The demo is all.
So what we are going to do next, we of course need to collect more data so we can get some good results. And we want to correlate the metrics we collected from the storage backend, from the node exporter, and from the applications, and trying to find out problems using this data. And there are some other algorithms that we can consider in the future, like random forest and autoregressive integrated moving average and so on. And we'll continue the journey to the autonomous data platform. So as I said earlier, we are right now at the early stage, the first stage. So eventually we are hoping to build a data platform that is self-managing and self-optimizing. Thank you. Are there any questions?
So thank you for the talk. It's really interesting. We are also working on anomaly detection in Red Hat. So I would be interested whether your tooling that you showed the whole system with Prometheus and the anomaly detection training and stuff, how general it is, how reusable it is for different kinds of metrics, maybe not just storage, or combining metrics from storage and other metrics from the cluster, from Kubernetes cluster and applications and stuff like that. If there is a potential for reusing it for other use cases as well.
Yeah, so right now we are just focusing on storage, so what we're collecting from different storage backend. But I also mentioned that we are also trying to collect metrics from the applications like the MongoDB, right? Yeah, so we, and then also from node exporter, so we do like to look at the data from different angle, try to correlate them. Yeah. Anyone else?
As I know, for now, state group, we will not support to limit the IO for per process. So in SDS project, we consider how to limit the IOPS for
How to limit the IOPS?
Yeah.
So yeah, no, we haven't really get to that stage yet. So what we have right now is basically just to collect metrics, and then the root cause analysis will be coming next, and then trying to find out problems, and then trying to figure out how to improve the system that will come next. So we haven't really get to that point yet.
And there is alert, but how to deal with the alert?
So that's the second. Yeah, so yeah, definitely we will get there. So, but we are really not there yet. So if you look at here, right? So we are right now right here. So just collecting the data, but then anomaly handling. So that's the next. So what do you do with those data, right? So right now we are just at the data we collected and we get alerts, and then, but I definitely get your point. That's actually even more important because you could get too much data, and what are you going to do with it, right? So it's very, very important, yeah. But we will definitely look into that next.
Yeah, I mean, in your node, you may just have one VG, right? So the IO can be, they can compete with each other. So, so how to do the limitation of the LPS, I think is a critical issue for how to do the storage production. So thank you.
Okay, thanks. Okay, I think time's over. Thanks, everyone.
Thanks.